Good morning to everyone. Today, I am going to represent Unit 2 in Information Theory and Coding, Data and Voice Coding. Okay. So now, what is voice coding means? Data and voice coding. So here, what is voice coding and what is data code? Okay. So data coding, it refers to the method of it representing the compressing and transmitting the digital data efficiently and accurately without any loss. Okay. So it is also called lossless coding. Okay. So what is lossless coding means? No information is lost. So for example, we are going to send 1,000 number of bits to the receiver side, but the receiver receives all the bits without any loss. This means lossless coding. Okay. So no information is lost between the transmitter and receiver, and original data can be perfectly reconstructed. Okay. We receive the original information. Okay. Then what is voice coding means? It is specialized in audio signal processing for compressing and transmitting speech efficiently while maintaining intelligibility and quality. So the same thing without any loss. Okay. So what are the goals in voice coding means? It reduces bit rate for transmission and storage, and it preserve the intelligibility and handling noise and channel errors. Okay. Then moving to pulse code modulation. What is pulse code modulation? So here, before going to the pulse code modulation, what is modulation? So just we know what is modulation. So modulation is the process of varying one or more parameter. That means the amplitude or frequency or time. Okay, so we varying one or more parameters of carrier signal in accordance with the modulating signal, instantaneous signal. That means modulating signal means here we means the message signal. Okay, both are same. So the original information signal or baseband signal or message signal or modulating signals are same. Okay. So here this modulating signal or message signal which is being transmitted for the communication, and the carrier is a high frequency signal here, and modulating is a low frequency signal. Okay. So this carrier signal has no data, but it is used for long distance communication or transmission. It is used like a carrier. Okay. Carrying the information. So there are many modulation schemes here, classified type of modulation employed. The digital modulation technique is the modulation. The pulse code modulation technique is the digital modulation technique. So here, a signal or pulse code modulated, it converts into analog information into binary sequence. So analog signal, it is voltage or current, it is converted into binary sequence like zeros and ones. So the output of pulse code modulation will reassemble a binary sequence. So we represented in the figure also. So see this figure, sine wave input, this is the pulse code modulation output. So this is the sine wave input and pulse code modulated output. So here instead of the pulse train, here the pulse code modulation produces a series of numbers or digital. Digitally it represents or digits, and hence this process is called digital. And each one of these digits through in a binary code represents the approximate amplitude of the signal sample at the instant. Okay. So the pulse code modulation here, the message signal or modulating signal or baseband signal is represented by a sequence of coded pulses. So this message signal is achieved by representing the signal in discrete form. So discrete means here the binary, it represents binary numbers, zeros and ones in both time and amplitude. So what are the basic elements behind the pulse code modulation means? Here there are two things, the main thing. The first section is the transmitter section, the second one receiver section. Okay. So in the transmitter section, it consists of sampling, quantization and encoding. So which are performed in analog to digital converter section. Then the low pass filter prior to sampling prevents aliasing of the message signal. So okay, sampling we know the analog signal is converted into digital signal. The quantization means we quantize the during sampling the quantization process happen, then encoding the signal. Okay, these are the elements behind the transmitter section. Okay, then the receiver section here, the regeneration, that means the reconstructed signal. So the regeneration of impaired signals. So here we perform decoding. and reconstruction of the quantized pulse train. So this is the block diagram of pulse code modulation. So here see that these are the transmitter section. It consists of message signal, low pass filter, sampler, quantizer, and encoder. So after that it is applied through the channel. In between the channel, the regenerative repeater. Then after that, this is the receiver section. Okay, so this is the receiver section. Here regeneration circuit, decoder, reconstruction filter, and destination. Okay. So we are going to see about the explanation of these blocks. Okay. So first low pass filter. So before that, first the analog message signal. So here analog message signal means here voltage, current, speech or video or something. This is the analog signal. So it is applied to the low pass filter. Okay. So the low pass filter function is filter or eliminates the high frequency components, because low pass filter only allow the low frequency signal. So I already told our information signal also is a very low frequency signal. Okay. So here we can use the low pass filter. It will allow only the low frequency signal, our information signal. Okay. So it won't allow the high frequency component present in the input analog signal. So which is greater than the highest frequency of the message signal, the original signal, to avoid the aliasing of the message signal. Okay. Then the low pass filter output is applied to the sampler. So sampling, here this is the technique to help collect the sample data at instantaneous value of the message signal. Okay, so it will reconstruct the original signal. Okay, so the sampling rate must be greater than twice the highest frequency component W of the message signal in accordance with the sampling theorem. So this is the sampling theorem. So here the sampling means first we are going to convert the analog input to the digital one. Okay, so that means the digital one means binary zeros and one. It converted into zeros and ones. Okay, so it divided the analog signal into the many samples, the sample data at instantaneous values of message signal. Okay, so this will be, so the sampling rate must be greater than or twice the highest frequency component W of the message. Message means the original input signal. So in accordance to the sampling theorem. Okay, then the sampling output is applied to the quantizer. Here, the quantizing is a process of reducing the excessive bits and confirming the data. So, the sampled output when given to the quantizer, it reduces the redundant bits and compress the value. Okay. So, after that, quantization means here approximation. It will approximate the value. Okay. Then it is applied to the encoder. Okay. So, here, the digitization of analog signal is done by encoder. So encoder, it designates each quantized level by a binary code. The sampling done here is the sampling and holding process. So there are C section, LPF, low pass filter, sampler and quantizer. Both section contains, it will act as an analog to digital converter. So we combined these three components, low pass filter, sampler and quantizer. We called it as an analog to digital converter. So the encoder, it maximizes the bandwidth used. Then it is applied to the, so the transmission section over, then it is applied through the channel. So here the regenerative repeater is connected in between the transmitter and receiver. So why we use this regenerator repeater means this regenerator repeater increases the signal strength, because once we send through the channel strength will reduce because of noise in between the channel. Okay, so we need to boost the signal strength of the input signal. So we have used the regenerative repeater in like a distance of the 100 meter ones or 50 meter ones. So once we can use the regenerative repeater in long distance communication. Only it is used for long distance communication. Okay. So the output of the channel also, once a regenerative repeater to it compensate the signal loss and reconstruct the signal, and also it increases the strength. So the main purpose of the regenerative repeater is it will boost the signal strength of the input signal. Okay. Then it is applied to the strengthened signal is applied to the decoder. Okay, the decoder in the receiver side, receiver section. So the decoder circuit decodes the pulse coded waveform to reproduce the original signal. So this circuit acts as the demodulator. Okay. So the transmitter and receiver section over. So finally we got the original recovered, reconstructed input signal, the information signal. Okay. Then what are the advantages in pulse code modulation? So why we use this pulse code modulation means it is robust against noise and interference. Okay. So that means in pulse code modulated signals are less susceptible to noise and interference compared to analog signals. So compared to analog signals, the pulse coded modulated signal have a very less noise and interference. Okay. Then the second point is uniform transmission quality. So the pulse code modulation provides consistent signal quality throughout the transmission process. So because we already told that regenerative repeater is used in between the transmitter and receiver. So in approximate distance, it will boost the signal, then transmit the signal. Again, in after 100 meters, it will boost the signal, then transmit to the signal. Okay, so the signal quality throughout the transmission, it is very consistent. Okay, then the next one is efficient signal to noise ratio and bandwidth trade-off. So the pulse code modulation allows for a good balance between the signal to noise ratio and bandwidth usage. Okay, then it produces a secure data transmission between the transmitter and receiver. So digital encoding makes a PCM pulse code modulated data more, it is secure. So this in security purpose, we can use pulse code modulation. Then efficient regeneration, data transmission. So that means digital encoding makes PCM data more secure. Okay. Then efficient regeneration. So here PCM signals are easily regenerated to eliminate accumulated noise. Okay. Then easy to add and drop channels. So multiplexing, demultiplexing channel is simpler in pulse code modulation. Then what are the drawbacks in pulse code modulation means here overload appears when modulating signal changes and overload can occur between the samplings if the changes is greater than the step size. Then large bandwidth is required for the transmission. That means it typically required wider bandwidth compared to the other modulation techniques. Okay. Then noise and crosstalk only exhibit a low attenuation but can rise. So while generally robust and noise crosstalk can be still it is a factor. Okay. Then integrated digital network can also only be realized by the gradual extension of noise. So here implementation within this IDN can be complex. Okay. Then the next one is very important, quantization error between the quantizing process. Okay. So the difference between the original analog signal and translated signal is known as a quantization. So the difference in between the original signal and received signal is known as the quantization. It is error. So here, then what is the bandwidth of pulse code modulation? So here we assume W of t is bandwidth limited to capital B, it's a hertz bandwidth. Okay, the minimum sampling rate is 2B samples per second. And A to D, analog to digital converter output, it is equal to N bits per sample. Quantization level, it is equal to M. M represents the symbols, it is 2 power N samples. Okay. So you assume the sample PCM without redundancy. So minimum channel bandwidth rate, it is equal to bit rate divided by 2. So assume the bandwidth is B. Caps B represents the bandwidth. Sampling rate is 2B, that is twice the bandwidth of the modulating signal. Then the A to D output is N bits per sample. It is the quantization level. So here 2 power N bits, that M represents the symbol. So M it is equal to 2 power N samples. Okay. Then without redundancy. So you assume overall without redundancy, minimum channel bandwidth is a bit rate divided by 2. Okay. So the bandwidth of PCM signals, that is PCM, it is greater than or equal to NB with the sync function as orthogonal basis. So bandwidth PCM greater than or equal to 2 NB with rectangular pulses at the orthogonal basis. So for any reasonable quantization level, M represents the sample. The pulse code modulation require much higher bandwidth than the original W of t. Then what are the noise in affect the pulse code modulation? Here type of noise, quantization noise, environmental noise, and filtering noise. Okay, so this quantization noise during analog to digital converter, we already told what is analog to digital conversion means: sampling, quantization, and low pass filter. The three components included in the analog to digital converter. So after sampling, the quantization process, during the quantization process only the quantization noise occurred. Okay. Then environmental noise, then filtering noise. Environmental noise means electromagnetic interference. Then filtering noise is a low pass filtering at a decoder. Okay. Then type of quantization noise. So this in quantization period, the quantization noise occur. What are the types in quantization noise? Means overload noise, random noise, granular noise, and hunting noise. Overload means input is too large. Random noise input is too small. Then granular noise non-uniform and error jump. Then hunting noise is too long of quiet time. Then special quantizations are used for the avoiding these noises. MULA and ALA quantizers. Then the next one is differential pulse code modulation. So what does differential pulse code modulation means here? Pulse code modulation. So before going to see the differential pulse code modulation, what is the disadvantages in the pulse code modulation? Okay, so in pulse code modulation, the samples of the signals are highly correlated with each other. So the signal value from the present sample to the next sample do not offer by a large amount. Okay, so the adjacent sample of the signal carry the same information with a small difference. So when these two samples are encoded by the standard pulse code modulation system, the resulting encoded signal contains some redundant information bits. That means a similar informations are present in the input. Okay, so to process this redundant information and to have a better output, it is a wise decision to take the predicted sample value. So assumed from its previous output. So we can take the previous output value to the input and compare the signal. So and summarize them with the quantized value. Such a process is called a differential pulse code modulation signal. Okay. So the main thing is to overcome the disadvantage of pulse code modulation, we are going to process the differential pulse code modulation. It will compare the previous output with the present input. So this is the concept behind the differential pulse code modulation. Okay. So then the differential pulse code modulation is a technique of analog to digital signal conversion. So this technique it samples the analog signal and then quantizes the difference between the sampled value and the predicted value. Then encode the signal from a digital value. So before going to discuss a differential pulse code modulation, okay, so we see the principle. Okay, here if the redundancy is reduced, then overall bitrate will decrease. Okay, so and the number of bits required to transmit one sample will also reduce. Okay, so suppose we want to reduce the redundant bits now, definitely the overall bitrate and decrease, and the number of bits required to transmit to one sample will also reduce. Okay, so this type of digital pulse code modulation technique is called differential pulse code modulation. So the DPCM work on the principle of predicted value. So it will compare the predicted value. So the value of present sample is predicted from the previous samples. So this prediction may not be exact, but it is a very close to the actual sample. Okay, it is not more difference. It's a slight difference between the predicted value and input value. Okay. So this is the DPCM transmitter, differential pulse code modulator transmitter. So here we see about the sampled input. We called it as X of NTS. The quantized value we can say NTS. So X of NTS. So this is the comparator plus and minus. So here the sampled input is applied to here and the predicted value is applied. That means the quantized value is applied to here. So both signals are compared. The output is applied to the quantizer. Then the quantizer output is applied to the, again the previous input is taken to the input. So the predicted value is compared with the present input. After that it is applied to the quantizer. The quantizer output is encoded. Then we got the DPCM, the differential pulse code modulator signal. So this is the implementation of differential pulse code modulation. So this is the transmitter section. The same thing, the only difference is the predicted value. The difference between the pulse code modulation and differential pulse code modulation. So here analog input is applied to the low pass filter. So we know about the function of low pass filter. The low pass filter only allow the low frequency signals. It won't allow the high frequency signal. Then the plot topped PAM, here this the PAM signal is applied to this comparator. So here the same process in pulse, the differential pulse code modulation in transmitter. So here the predicted output is applied here. Okay. Then both signals are compared, the input signal and predicted signals are compared. Then the output is, the difference is applied to the quantizer. So the quantizer quantizes the signal, approximate the signal, then it is applied to the encoder. Encoder encoded the signal, then it is applied through the channel. The channel in between the transmitter and receiver. Then in the receiver section, here regenerated circuit, then decode the signal, then again reconstruct the same block diagram is used in here, predictor one. The same signal is in a reverse manner. Okay. So after that, we are getting the original reconstructed input signal, or that means it's a differential pulse code modulated signal. The quantization here, the another implementation of DPCM, the same figure is so reconstructed, and this is the same thing one. So here we can use the reconstruction filter. The difference is here the low pass filter is applied before that. Okay.